The topic is the impact test in the EN 1651, which is the European standard for paragliding harnesses. On the menu, first a description of the test, then an explanation of the current criteria, and finally a possible improvement, the SIC criteria. And yes, a decent stock of chocolate is recommended for this video. What is the goal of the impact test in the EN 1651? The objective is to assess comparatively the capacity to attenuate the compression force transmitted to the spine of a pilot in an event of a vertical fall under the rescue parachute. I will decorticate the important terms one by one. It is just an attenuation, it's not a suppression, it's clearly not a guarantee of no injury. We are only talking about the spine, not the hip, pelvis, or any other body part, just the spine. Also, we only consider compression stress, not flexion, bending, or any other kind of situation that can also create damage. The fall is in a vertical plane, considering the spine having a 22.5-degree angle with the gravity. This is not a front or a side impact. The test is fully guided. The parachute certification set a maximum vertical speed of 5.5 meters per second. You might find that is very limited, and you are right. Impact test from the EN 1651 version 2020 is just that, not more. Many of these choices are made to improve the repeatability of the test, for example, the fact that it's fully guided. Let's look now how it's realized. Here is the ground. Here is a dummy with a mass of 50 kg. This value comes from assuming an 80 kg pilot with 30 kg of leg that has already touched the ground at the moment of impact, so only 50 kg are actually supported by the spine. Now we lift the dummy to 1.65 meters. This corresponds to a theoretical impact speed of 5.5 meters per second, which is the maximum vertical speed allowed for a certified rescue at sea level. The harness is now fit to the dummy, so the impact pad is positioned under the dummy. An accelerometer is placed inside the dummy to record the acceleration along the vertical axis. Then it's dropped. This is how it looks like in reality. Let's have a look at the recorded data. X-axis is the time, and Y-axis is the recorded acceleration. This part is the static phase before being dropped. Here's the free fall at -1 g. Now comes the main impact, the one we will measure later. The harness is back in the air for the first rebound, and then the other rebounds, which we will ignore. On the next part, we will zoom on the first peak, trying to understand more the criteria. This is a zoom on the first main peak again. X-axis is time and Y-axis is the recorded acceleration. I will list the criteria that the impact pad should fulfill to pass the 2020 version of the EN. First, the maximum acceleration recorded should be lower than 50 g. We will also look at the duration above 20 g to be less than 25 milliseconds. In this case, 24.2 milliseconds at 20 g. The duration above 38 g should be less than 7 milliseconds. These three rules together delimit a border, and the acceleration curve should be completely below this line, in this green area. All these criteria come from the same study in 1959, Human Tolerance to Rapidly Apply Acceleration by Martin Eiban. Eiban and his team studied different cases. One of them is very interesting for us. It's this one, with the acceleration coming from the bottom. X-axis is the time and Y-axis is the acceleration. Be careful, both axes are in load scale. In the middle, there is a dozen of data points. We will recreate this graph. It will be more readable and I will explain it more in details. This part is the core part of the video. Grab some chocolate bars and brace yourself. First, we draw the axes as usual, except by this time, because the values are spread across several orders of magnitude, we will use log scale. It doesn't change much. During this study, humans and animals were exposed to different acceleration from different duration. For example, this point on the graph represents a human exposed to 10 g during 0.1 second. Now we have the other data points. There are some hogs, human, and chimpanzee. Searchers observe the injuries in each case, and they define 3 areas: small injuries, moderate, and severe injuries. Side note, this study was also used to determine the optimal acceleration that can be used for a jet fighter ejection seat. And the more important for us is this line, showing the EN 1651 standard limit. Harness should be below this curve. Keep this graph in mind, as we will use it again later. Now that we have the criteria in mind, we can compare different impact pad response. Time to call back our best friends, the axes. Here are 3 impact pad response to a EN drop. Let's try to identify the safest one by comparing them pairwise. For this first pair, the green curve has lower G and a shorter duration at every G level, so the green is the winner. For the second pair, they have the same max G, but the green curve has a shorter duration at every G level, so the green wins again. The last pair is a bit trickier. Here, the orange curve has a lower max G, but a longer duration at 20 G, for example. Which one is the winner? How can we compare G and time? Who sets the exchange rate between G and duration? There is a full family of criteria based on an interesting idea: integrating acceleration over time. This approach is or was used in a medical diagnostic for head, thoracic, and soft tissue injury. In sport, it certifies bouldering crash pad and evaluates running shoes performance. It also protects soldiers from blast and workers from chronic vibration exposure. Inside this family, there is one criterion that will prove to be a useful tool in our quest to determine which curve is the better, the blue one or the orange one. It's the head injury criterion, HIC. It's a mathematical tool developed in the 1970s based on research into head injuries. Here's the formula. The WG6, the group in charge of the EN standard, reused the basis of this formula, change the name and adapt the exponent to our paragliding usage, and the HEC became the SIC. Let's discover it more in details. Let's bring back the formula and break it down part by part. To be honest, this section is more for mathematics enthusiasts, but is not a prerequisite for the rest of the video. That's the size of the rolling window. This is the average. Then we squared and multiplied the average acceleration by the width of the window. And this part means that the result will be the maximum value of this formula as it is run along the entire curve. A visual interpretation is always better. For a given acceleration curve, a time window is selected. That is the average over this window. The average value will be squared and multiplied by the size of the window. The SIC measures the severity of impact by considering both magnitude and duration of acceleration. We will do it on a real drop curve. On the top right, the resulting SIC curve. This is our sliding window. Using the formula, we compute 1 point on the SIC curve, here, the red points. Now look, the window is sliding and for each step, an SIC is computed. generating the SIC curve. The final SIC value will be the max of this curve. If we look back at our two curves blue and orange, we should now be able to differentiate the worst one. That is the max G and the duration at 20 G, and the dashed line are the compute SIC curve for each drop. So the orange has an higher SIC, and the orange lose. In this case, the additional duration is more damageable than the extra max G. I want to go back to the A-band graph and see how the SIC formula integrates. By setting a max SIC value, we delimit a line on this graph, the purple one. By changing the exponent, we can adjust the slope of this limit. Now, if we change the criteria, we translate this line. This is the current EN limit. I find it beautiful that we can observe the implication of our formula in this reference graph. I feel like we have landed back on our feet. I present you one criterion, the SIC, but it's worth mentioning that other approaches are possibly promising, especially the dynamic response index, DRI, plus of course all the one I'm not aware of. Regarding the future of the EN standard, it's currently under revision. The first draft has been circulated in 2025. After the first comments, WL6 decided to reopen the topic, to improve the criteria, and to add another test position, more lean back. I insist on the fact that is my current personal understanding. I allow myself to update it and change my mind as new information or evidence comes in. Anyway, I guess you finished your chocolate stock. It's time to say thanks to all the people which help on this topic. Thank you.